We get to the hidden concentration village only to be greeted by a villager by the name of Haku, who was once used by one of the swordsmen, Zabuza. Now, wanting to make amends, Haku has provided imperative intel that will allow us to win the battle. Haku wants to make this quick so that we can head to battle soon. They state, mixing concentrated and dilute solutions create an intermediate concentration. And a concentration cell is a voltaic cell that utilizes different concentrations of species in the same half reaction in separate cells. Another way to say that is it is a voltaic cell in which both compartments contain the same components but at different concentrations. And since we are in separate half cells, then of course we have the ability to have spontaneous electrical energy be generated as we go from the anode to the cathode, and therefore the cell can perform work until concentrations end up equalizing. Get into this example of our copper, write this here, copper 2 plus half cells here. Now, the concentration cells are a type of voltaic cell, okay? So it's still going to have the same setup as a voltaic cell. The difference is, as you can see, the anode and the cathode is both copper. And also the electrolyte solutions are both copper. Copper 2 plus here, copper solids for the electrodes. But the actual concentrations are different. Now, since the concentrations are different, then that means that we know we are outside of standard conditions. And so if we're outside of standard conditions, okay, our standard E of the cell will be 0 here. Okay, folks? Now let's check. If we know our standard cell potential is equal to our standard cathode minus our standard anode, and they're both copper, then it's going to be subtracting by one another, and they're going to be 0, right? And so when we're outside of standard conditions, we're focused on the Nernst equation again and our non-standard cell potential. So in concentration cell, non-standard cell potential is non-zero due to different concentrations, despite the standard being 0. Okay, folks? So for instance, we have our concentration cell here, and we're starting with 0.10 molar of copper 2 plus in the anode and 1.0 molar of copper 2 plus in the cathode. As you can see, if I just move the decimal place over 1 here, that the cathode is a 10-fold higher concentration than our actual anode here. Okay, folks? Now, the Nernst equation is actually going to help us provide the amount of voltage that's created for this overall concentration cell. So we plug in our overall equation. So to find a non-standard cell potential, we already know our standard cell is going to be at 0. Our number of electrons that are going to be transferred are based on the half cells in the overall concentration cell here. So there's 2 electrons here, there's 2 electrons. It's the same exact half cell. One is reversed for oxidation. So our overall reaction is going to be Cu2 plus aqueous 1 molar. It's going to give us Cu2 plus aqueous 0.10 molar. So for our N value, that's going to equal 2. And for our Q value, it's going to be our product divided by our reactant. So Cu2 plus in the 0.10 molar concentration divided by our Cu2 plus in the 1.0 molar concentration. And we can actually see that here. We can call this the more dilute version versus the more concentrated version. So I actually have the Nernst equation written here. We know this is going to be 0, so that's plugged in here as 0. This is 0.0592 divided by 2 now, and this is log of the diluted concentration divided by the concentrated version. So this is going to be 0 minus 0.0592 divided by 2, log of 0.1 divided by 1.0, okay? That means it's equal to 0 minus, of course, this value, minus 1, and overall we get 0.0296 volts. So that means our non-standard cell potential is 0.0296 volts. And this shift is going to occur as the system moves towards equilibrium, okay? Equalizing concentrations in both half cells. So again, we had started with different concentrations. As we go along, we're going to generate electricity. And then, of course, we have that particular voltage until we reach equilibrium, or of course, there is no voltage there. There's no more work being done. And the concentrations are equal. Here's just another version of the Nernst equation, just that is not handwritten by me. That's a little bit cleaner for some folks. All right, folks? Haku then wants to review quickly how a concentration cell works to wrap it up for us. So in a concentration cell, the anode is going to be in the dilute half cell, as we can see is a 0.10 molar Cu2 plus concentration initially, right? And then as the copper atoms are going to be releasing electrons, that's going to lead to an increase in the Cu2 plus concentration for this half cell. Those electrons are going to release. They're going to be, of course, having the voltage. And of course, in our cathode, or a concentrated half cell, the copper 2+ ions are going to accept those electrons, and it's going to cause the copper atoms to deposit onto the electrode here. What's going to happen? You're going to end up getting a decreased solution concentration. This process continues until equilibrium is reached with equal concentrations of the Cu2+ ion, okay, folks, in both half cells. This is going to result in a decrease in the non-standard cell potential, similar to any voltaic cell. Now, of course, if there was no external circuit here, no electrodes, and these two solutions were mixed, the final concentration will still be the same, but there will be no electrical work that will be generated. Now, this is all the information Haku could give us in this short time, but it's definitely enough to defeat the 7 swordsmen if we combine what we already know. Let's battle, folks. Welcome to our first battle. We must fight to defeat the 7 swordsmen of the concentration cell village by answering this question. They want us to calculate the potential of a concentration cell. It says a voltaic cell consists of 2 silver plus half cell. In a half cell A, the electrolyte is 0.010 molar AgNO3. In half cell B, it is 4.0 times 10 to the negative 4 molar AgNO3. What is the non-standard cell potential at 298.15 Kelvin? So automatically I see the same species that are at different concentrations. I automatically start thinking, okay, we have to use what we know about concentration cells, which means we have to understand to be able to use the Nernst equation. So because these two half cells are the same, the anode and cathode are both going to have the same values. And so our standard cell potential is going to be 0. This is still going to be 0 volts here. Now let's go ahead and think about the other portion so that we can get our non-standard cell potential like the question 1. All right, so let's now focus on the half reactions. We know our voltaic cell is going to consist of the silver and, of course, silver ions. So this is going to be our solid here, and this is going to be our aqueous. They told us that in half cell A, we have a concentration of 0.010 molar of AgNO3. Of course, our NO3 minus is not something we're focusing on, so when we disassociate this, we're mainly focused on our Ag+. And then half cell B, it has an Ag+ concentration of 4.0 times 10 to the negative 4 molar. So obviously half cell B has a lower concentration of silver silver ions than half cell A. But from our understanding, we know that reduction always happens at the cathode, making it positive. So we want to go with the most positive value, or you can always say the most concentrated value is going to happen with reduction. So when I'm looking at half cell A and B and I'm thinking of a concentration cell, well, okay, the higher concentration has to be reduction at the cathode, because that's going to be the more positive number. That means that half cell B is going to be oxidation. I don't know why I'm writing a Q. Oxidation at the anode. And now our concentrations here make sense. This is our anode, right? And this is our cathode. So the reaction is spontaneous because you have a decrease in the Ag+ concentration in A and an increase in the Ag+ concentration in B, so that the silver here can deposit onto the electrode. Next, we can go ahead and write our half reaction. Of course, since we already know we're dealing with one single electron that's being lost, and it's the same exact species that we're dealing with, which is just straight up silver, then we can just straight up write I always write my reduction one because I'm used to seeing it in all the standard tables that we're used to. So I'm going to write my reduction and then I'm going to reverse it to get my oxidation. So I write my Ag+, and let me rewrite this to make it look better. I have Ag+ here, and I'm showing that it's going to gain an electron. And what I wrote at the bottom here is just going to be aqueous, and then I write the concentration, just so that it's specific, because remember, I'm using the same species, so you have to make sure the concentration is specific. And then I'll just do the reverse here. I'm starting off with Ag solid, and then I'm going to be producing Ag+, but this time it's going to be aqueous, and it's going to be the 4.0 times 10 to the negative 4 molar. And of course, we're going to have an electron being lost here. There's nothing to balance as far as electron charge because we're just simply losing 1. So automatically we know our N is going to equal 1 here. And then in order to get our Q value, we need to make sure we get an overall reaction here. So we're going to get rid of our electrons, and that means I'm going to have my Ag+ here at the 0.010 molar. And then I'm only left with Ag+ at the 4.0 times 10 to the negative 4 molar. Why? Because our Ag solids are basically going to cancel along with our electron. And here's what that overall reaction looks like written out. So I'll have Ag+ at the 0.010 molar is going to form Ag+ at the lower concentration. And so these are my products, and this is my reactant. I can go ahead and solve for my Q value, and I can take my diluted concentration divided by my more concentrated version of my silver, right? Exactly like we saw when Haku was speaking to us previously. I went ahead and solved for my Q value. I took my diluted concentration, which is going to be my product here, 4.0 times 10 to negative 4 molar, divided by my reactant. The concentration here is 0.010 molar. When I divided these two numbers, I get 0.040. Okay, and then I took the log of that because I already know I have to do that for my Nernst equation, and I got negative 1.39794. Now I have all my numbers. My Q value, I actually have the log of Q here. I have my E naught of the cell, or my standard cell potential, and so I can go ahead and solve my E of the cell, which is basically my non-standard potential. Okay, folks, so I'm going to erase some of this here and get to it. All right, so my non-standard cell potential is going to equal 0 volts minus, if I just take 0.0592 divided by 1, I simply just get 0.0592 volts, multiplied by my log of Q, which I already found as negative 1.39794. So I'm going to go ahead and multiply these two numbers together, and I get negative 0.082758048 volts. Of course, I'm going to add that to 0, and I get 0.083 volts as my final answer. This is the non-standard cell potential of the Ag plus half cell. We did it. We defeated those terrorizing the hidden concentration cell village. We were gifted with Jitsu and scrolls for our journey back home, and the connection between hidden voltaic cell village and the concentration cell village have been restored, demonstrating the connection between concepts, techniques, and of course between the two villages. See you back in the hidden chemistry village.